there are an infinite number of primes. But how do we know this? How can we prove this? There's Euclid's proof, which is very, very famous. I'm sure you've seen it. There's Euler's proof. This is another one. This is very interesting, and this deals with analysis. I guess you could say that it's part of analytic number theory. This is the one I'm really interested in. This pertains to the topic we've been talking about, Euler-Mascheroni gamma, log, all that stuff. It's very similar. But in this video, I will start off with Goldbach's proof. Goldbach was a friend of Euler. I will give you this to think about while I continue working on Euler's proof, which is a little bit more involved. Goldbach's proof is very, very beautiful. And I think it's just amazing and it's worth knowing. So let's start with this. The idea behind Goldbach's proof is this concept, a coprime sequence. Let's take a finite sequence AK from 1 to n, m. This is A1, A2, all the way up to AM. And this is a coprime sequence if any two of these that I choose, any two, like this and this, are coprimes. So I can write that like this. The GCD of AJ and AK is 1 for all of them, except when, of course, when J and K are equal. Okay, so when J and K are not equal, the GCD is 1. And J and K are from 1 to n, 1 to m, like so. Okay, so that's a coprime sequence, very special sequence. So here's a proposition. This sequence, if we take all of these numbers and look at them, these numbers must have in all at least m distinct prime factors. So let's prove this by contradiction. Let's assume it's not true. So we will suppose there are m-1 prime factors. Let's represent the primes by a box, and we'll represent the elements of A or AJ like this as a dot, like so. And we're going to fit a dot into a box if P divides A. So what does this mean? So this, if I have A in here, that means P divides A. Great. So I have some interesting possibilities. If I have two primes, let's say P1, let's say 3 and 5, and I have the number A is 15. Well, in this case, 15 can go in here, but also 15 should go in here. So it's possible to have the same dot in two different boxes. So this situation is a little bit different from the usual pigeonhole principle, because I can actually have like a quantum pigeon which can be in two boxes at the same time. So quantum pigeon is possible. However, the next one here, this is not possible. So I have here 15 and here 25. So I hear two dots in one box, 15 and 25. This is no good because here 15 and 25, the GCD is not 1, the GCD is 5. Okay, so that's no good. So I cannot have two pigeons in one box. So this is like Fermi exclusion principle. So I can't have two electrons in the same, I can't have two pigeons in the same box, but I can have quantum pigeons that are in two different places at the same time. So this is very interesting. So now let's draw all of our boxes and see what happens. I have m-1 prime boxes. But in all, I have, how many of these blue dots do I have? Well, I have A, J goes from K is 1 to M. I have big M. I have M dots. I have M pigeons that I've got to put in those boxes. And sometimes I can put the same pigeon into two different boxes. So there's no way to do this. I'm going to end up, okay, I fill up at least m-1 boxes, but then there's one left over. So sooner or later, I have to have another pigeon in the same box, and that's not allowed. So this is a contradiction. Okay, great. So I need to have at least m prime factors in that sequence. And that leads us to the following interesting observation. Suppose now we have an infinite sequence and it's coprime. So any two elements are coprime. Well, this will imply that there's at least an infinite number of prime factors. Yeah, so let's repeat that. This is the key idea. If I can find such a coprime sequence that's infinite, well, there must be an infinite number of different prime factors. I should put that here. It's different, distinct prime factors in this sequence. So the idea of Goldbach's proof is to find such a sequence, which Goldbach did, and I will show you how he did it. Fermat numbers are a sequence of numbers that was discovered by Pierre Fermat, and they're very interesting, but not really for the reasons Fermat thought. It's a sequence that starts from 0, unlike the ones we're used to. The nth term looks like this, 2 to the power of 2 to the power of n. So it's like super rapidly increasing. So that's 2 power 2, 0 plus 1. That's 3. Okay, so that begins with 3. F0 is 3. So Fermat thought these were all primes, and it turns out this is wrong. However, you can use Fermat numbers to prove some things about primes, namely that there's an infinite number of primes. But let's look at what went wrong with Fermat's idea. Let's use maxima. So I'm going to switch to the terminal and do a little bit of computer stuff now. Here I'm in my editor VI, and let's write a little bit of maxima code. Fermat, and this is a maxima function. That's how you define a maxima function. Very easy to do. And let's create a convenient thing here. F of n is, okay, we'll make a list. The nth Fermat number, and then Fermat n, and then I want to see the factors. So we'll factor Fermat n like so. So that's telling me everything I need to know. All right, so let's run this in maxima. Yeah, very good. So f, okay, first we have to load that code. There we go. F of 0, what's that? Okay, 0's Fermat number's 3. That's no problem. Everything is nice. And now, what is the first Fermat number? First one is 5, and the prime factor is 5 because it's prime. Very good. And let's see, second Fermat number is also prime, 17. Hey, maybe Fermat was right. How about the third Fermat number? Third one is 257. That's prime. Fermat's right, man. Fermat's right. Okay, fourth one. Yes, very good. It's also prime. What about the fifth one? No, it's not prime. It has, let's look here. It has a factor. Whoa, what's that? Okay, some huge number just popped up. It has a factor of 641. Yeah, 641. And that was discovered by Euler, actually. So he factored this huge number. What about F6? Is that prime? No, it's not. It has a factor of 274,177. What about F7? Let's see if maxima can do F7. This might take time. Who knows? And I guess if I was in class right now, I would just be telling a story as the time goes by, And so let's see how much of this time goes by. Well, maybe I should embark on some travel story or something, or story about famous mathematicians or world history. Oh, there we go. Yeah, it's not prime. It has a huge factor, prime factor here. Yeah, it's not prime. How about F8? Let's see if maxima can do F8 and give me some feedback on F8. Is that prime? This might take a long time. I don't know. Well, actually, I do know because I've tried these things before. So let's see. Ah, yeah, there we go. So it's not prime. It has a very big factor. Now, F9 I know is going to take years to do, so I'm not going to try it. So the thing to notice is, just in passing, all of these prime factors have power 1. So in fact, all of our Fermat numbers seem to be square free, and that leads to some interesting conjecture I thought you might want to know. Let's talk about that for a minute also. And so we have some properties of the Fermat numbers. First of all, they're all odd because 2 power n is even, and when you add 1 to that, it's odd. And that Fermat was wrong. Not all the f of n are prime. And in fact, there's some unanswered questions about this. And just in passing, we seem to have discovered from computer that Fn are all square free. But as far as I know, this has never been proved, and it's still an open question. If you know more about it, let me know in the comments. All right, so now let's get to Goldbach's recursion, which is a very beautiful thing. When n is greater than or equal to 1, we have the following beautiful relationship. Fn is the product of all previous Fermat numbers plus 2. This is one of the beautiful properties of Fermat numbers. And this is the another one of the main ideas of Goldbach's proof. So let's prove this, and we're going to prove this by induction. I'll use my usual notation I like to use for induction. Capital P is a statement. PK is going to be this statement here. And this is a simplification. It allows you to easily write this statement over and over again. Otherwise, you'd have to keep saying it. So if I want to do a proof by induction, I need to do two things. I need a base case. I need to prove the base, which is going to be P1 because n is greater than or equal to 1. And I have to prove the induction step. So I assume that if Pk is true, I will assume Pk, then I have to prove that Pk plus 1 is true. So in fact, I'm not proving Pk, I'm assuming Pk is true, and then I'm proving Pk plus 1 is true. So I will leave some links to induction stuff that I have done before, and in fact, I think I have a playlist full of it. Okay, we have to prove the base case P1. So let's begin with this. Let's f0 plus 2. What's that? f0 is 2 power 0 plus 1 plus 2, so that's 3 plus 2, that's 5. But 5 is f1. And so therefore, I have f1 equals f0 plus 2. But this is, in fact, if you look at this statement here, this is actually P1. And so P1 is true. So I've done the base case. Now, B, let's assume Pk. So we assume that statement is true. So I have the following as a truth. So I know this is true by hypothesis. And now let's look at the following combination. So what I've done here is I've taken this and I multiplied it by Fk. And what can I do with this? Well, here I can apply Pk. I have my expression here. So I take this 2 here to the other side, and I end up with Fk minus 2 times Fk. Very nice. All right, so we just have to do some algebra here. Let's think about this. 2k plus 1 minus 2, and this is 2k plus 1. Right, and now I can subtract that, and I have here, look at this. This just magically works out to a difference of squares. So this is now 2 power k squared minus 1. So we just have to be really careful how we deal with these powers of powers. It's can be very confusing, but just be careful. 2 times 2k, that's the same thing. And this is 2k plus 1 minus 1. All right, so let's do some more magic. 2 to the power of 2k plus 1 minus 1 plus 2 minus 2. I can always add and subtract the same thing. So what do I have now? 2k plus 1. That's plus 1 minus 2. And this is f of k plus 1. So this is f of k plus 1 minus 2. Very good. So let's look at this. Combine this and this together, and what do we get? We have fk plus 1 is f0, f1, dot, 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 all the way up to fk plus 2. And this is pk plus 1. There we go. So we have proved that if pk, then pk plus 1. And so therefore Pn is true for all n greater than or equal to 1, all the natural numbers. Very beautiful, this Goldbach recursion. And in fact, there are many recursions for Fermat numbers. Here's one that you can prove as an exercise. F of n is f of n minus 1 all squared plus 1. And this should be true when n is greater than or equal to 1. So you try proving this by induction and let me know in the comments if it worked out for you. Now comes the grand finale. We will prove that the Fermat numbers are an infinite coprime sequence. Let's take any two Fermat numbers, fm, fn, and we will assume that m is less than n. And if not, then just reverse them. And so we don't lose any generality by assuming that m is less than n. Now we're going to use a little lemma, which I've used before. Let's say D divides the sum a plus b and D divides a, then D divides b. This is proved in Euclid, I think. So now let's assume that there is a common divisor. D divides f of m, and D divides the nth Fermat number also. And let's see where that goes. So let's write fn and use the Goldbach recursion, f1 dot, dot, dot. I'm going to put like a really big dot here. And then fn minus 1 here plus 2. Okay, great. And the interesting thing now is that we said that fm is less than fn. So m is less than n. And so that means fm must be in here somewhere in this part. So D divides fn, but also we must have this. Because fm is in this product somewhere, D must divide this term here also. And by this lemma then it must be that D divides 2. So D must be either 1 or 2. That's very interesting. Now, can it be 2? What do you think? It cannot be 2. Because it cannot be 2, because if it's 2, then 2 divides fn, and then therefore fn is even. And this is wrong because we know that all the fn's are odd. They're all of the form of an even number plus 1, which is, of course, odd. And so therefore, D is 1. And so therefore, for any 2 Fermat numbers, they are coprime. And so by proposition in the first part, there are an infinite number of primes. We can say this in a kind of more poetical way. An infinitude of primes. I like that. That's really cool. Well, there you have it. That is a super beautiful proof. So elegant, so many beautiful ideas. It turns out that Fermat numbers have redeemed themselves. You would think, it doesn't work as a way to generate primes, but it comes back and it redeems themselves as a way of proving something else about primes. So I think it was just very beautiful. This is an absolutely classic proof. Goldbach is a genius. I love this. Anyway, it's a great introduction for what's coming up next, which is Euler's proof. I hope to get that done. It's a bit technical and requires some thought, but it's going to work out. And I hope you like this video, and like, subscribe, comment, write me something. It's always interesting to read these comments. And I will see you next time.